Swayam Prabha. Digital India. Educated India.
We started with logic as the first topic in this course because it's going to form the vocabulary for stating all the various results in subsequent topics formally, as well as being able to give proofs for various results in those topics. So now we go on to see what these proofs should look like. So, all these results that we are going to see coming up in later topics, they're all deduced using logic. And typically we think of using logic to make these deductions as a human endeavor, though it can be automated when the system is relatively simple. And the proof is something that accompanies this deduction as a means to convince others and even yourself that what you deduced is a correct result. Okay, and the idea is that the proof should be very easy to verify, very easy in the sense that it's a mechanical process to verify a proof, or ideally it should be. Of course, when we write a proof in real life, we don't write it to a level of detail that makes it machine verifiable, automatically verifiable, but conceptually that's what a proof should be. It should be automatic, it should be pretty mechanical to verify the proof. All the cleverness goes into coming up with the proof, and that is usually not automatable, even though there are theorem provers out there that can help you with figuring out what's the next step you should take. Okay. So what are we proving? Going back to the terminology from logic that we used, we are proving propositions. Okay. But these come under various names, theorems, lemmas, or claims, or whatnot, under, depending on the application you have in mind for those propositions. And these propositions are stated using various predicates that are specific to the system you are interested in. And these form the definitions in the system. For instance, a claim like all positive even numbers are larger than 1. And if you write it in symbols, this is what it could look like. It says for every x in z, where z is the set of integers, or what I'm calling numbers here. And the proposition then is that for every x in z, if x is positive and x is even, then x is greater than 1. And x is positive and x is even, they are written in terms of predicates positive and even, and greater is also a predicate for over pairs of integers, right? So these propositions we are trying to prove, they will be stated in terms of these predicates, and the proofs we are trying to come up with for them can use other propositions. So these are axioms in the system. For instance, a simple arithmetic system could have an axiom like all x in z, x plus 0 equal to x, right? So these axioms would be specific to the system. In fact, the axioms are essentially what define the system. And for us, these systems would be things like integers or more complex objects, systems of more complex objects like graphs that we would see later on. Okay, so that's what we are trying to prove. Propositions defined in terms of predicates in the system. And how are we trying to prove it? So here is what an abstract anatomy of a proof looks like. So when you are writing a proof, you should first state what is the proposition that you're going to prove. That's just to help the reader, the human reader, understand what you're going to do. And those are especially important if you're going to prove not the proposition that you are expected to prove, but some other proposition which you have shown to be equivalent to the original proposition. So if you rephrase the original proposition, you should clearly state that. And then the proof essentially consists of a sequence of propositions. So P0, P1, and so forth. That's a sequence of propositions where for any proposition in this list, Pk, either Pk is an axiom that's already there in the system, so you can just put it there in your list, or it's a proposition that has been proven maybe by someone else as a lemma that you can just refer to. So instead of copying their entire proof, you are allowed to refer to a proposition that is already proven and well known, let's say, or something you can cite. So you're allowed to do this also. You're allowed to put a proposition that already has a proof that is not part of the sequence P0, P1, Pn. And another thing you're allowed to do, and this is an interesting thing you're allowed to do, is to stick in an pk which you deduce from all the propositions sitting in your list so far. So if the propositions p0 up to pk minus 1 taken together implies pk, then you're allowed to put in pk. So what do I mean by these propositions implies pk? This is exactly when this proposition is true. So this what's here highlighted is a proposition saying the conjunction P of P0, P1 all the way up to Pk minus 1 implies Pk, right? That's a logical proposition. If that proposition is true, then you are allowed to put in Pk as your next proposition in this list. Okay. So even though I said, all of these things, the conjunction of all of this implies Pk, typically you would just take a couple of them, right? You would take some, Pi and Pj and say, oh, Pi and Pj implies Pk. If that is the case, then automatically a bigger conjunction involving Pi and Pj also implies Pk. This is something I should verify formally for yourselves. But, typically in a proof, you would not have to use all the statements you made so far to derive the next statement. However, you should point out which are the statements you're using. So you would say something like, Pk is implied by this Pi and that Pj. You should give an explanation so that the verifier can simply go and do a simple logical operation to basically verify this is true. Right? They should be able to easily verify it. And the level of ease is what defines the level of detail of your proof. If you are expecting your reader to be fairly sophisticated, you may not write down all, you may write down Pi and Pj implies Pk, and it might take some work to convince, for the verifier to convince themselves. But conceptually, this should be a derivation that you can do just using propositional calculus or the logical calculus we have seen so far, right? Okay, so that's what each step looks like, and at the very end you reach the proposition Pn, and that should be the proposition you are supposed to prove. Of course, this may not be such a linear process. In between, you might go out and prove some lemma and then come back and use, continue your original line of argument. For instance, you derived up to some proposition Pk minus 1, and then you said, okay, I'm going to prove Pk separately. And once you've proven it separately, you can now bring it and add it to your list. For instance, suppose Pk says this thing, Pk minus 1 implies P for some other proposition P. So that is what, suppose you have proven as a lemma. Now you can stick that to the end of your list. And then you look back at the list and you see Pk and Pk minus 1. and together they imply P. Again, you should quickly check this for yourself. If pk says pk minus 1 implies P, so that's pk, then pk minus 1 and that pk implies P. So this is this proposition is always true. So you should, there's a true formula. You should convince yourself of that. Okay, so that's what a general proof would look like, a sequence of steps. So here's a quick mental picture of there's a universe of all propositions sitting around. Every proposition is either true or false. And the green ones are true propositions, the orange ones are false propositions. So for every proposition, its negation will have the other color. But the trouble is there are a bunch of propositions which, just looking at it right now, you don't know whether it's true or false. There are a bunch of propositions that just by looking at them, you already know they are true because they might be the axioms, they might be propositions coming from the definitions, or they might be propositions proven earlier, well-known propositions, let's say. So they're all the green ones you can start with. But say it is a proposition out here that you're interested in proving. So the proof would look like, you pick some proposition P0 that's already known, P1 that's already known, and then let's say you picked a proposition P2 that is not known to be true. And here is where you will need to use the non-trivial deduction step, right? So I'm using the double arrow to indicate that the conjunction P0 and P1, so everything you proved so far, you listed so far, implies P2. So that's what this double arrow indicates. So you can take that step and now you can list, add P2 to your list. Now I changed it to green because now you know it's true. And then you can take another step, and that will be your P3. Again, the double arrow indicates that it's implied by P0, P1, and P2 together, and so forth. Right? So you make a bunch of moves until you hit what you wanted to prove. Okay? That's what a proof is essentially doing, taking you through a bunch of propositions, and starting from propositions you already know are true until you hit the proposition you want to prove, such that at every step the new proposition you're adding to the list is something that can be deduced from the ones you already listed. Here's kind of an example of what a real-life proof would look like. I mean, this is again stuff you have presumably done before, you've seen before, but let's see what how it fits this picture I was drawing. So here in this example, our system is that of integers. So the set of integers is Z, and there are a bunch of operations. So again, I'm not going to formally define the system, even though in foundations of mathematics it's important to be able to define these systems from scratch. We will take them for granted. And here is a definition I'm introducing. Basically, I'm defining what an odd integer is. So an integer x is said to be odd if there is an integer y such that x is equal to 2 times y plus 1. Okay. Here I said if, but actually what I mean is if and only if. There's the only way an integer can be odd. Okay. So this is just convention. In definitions, you would just say if, even though what you really mean is if and only if. If I were to write this definition in the form of a proposition, here is a proposition that completely captures this definition. It says for every x in Z, x is odd if and only if there exists a y such that x equal to 2y plus 1. So this is a proposition that I get while I define, or it is the proposition that I can use as a definition of odd. Okay, here's a proposition that I would like to prove. It's not a definition or an axiom or anything. It states that if x is an odd integer, then so is x squared. Okay, So let's see. Here's what it formally looks like. X is for every x in Z, x is odd implies x square is odd. Okay. So let's see what a proof for this looks like. So this was my definition, and this is a proposition I'm interested in proving. Now, I'm trying to prove something holds for every x in Z. So a proof for this, which by the way, what I'm going to show you looks rather contrived and tedious. When you write it, it should be more readable, and it should have more English there than the notation I have here. So for this kind of proof, you start off by saying, you're interested in proving something holds for every x in the set. You would start off by saying, pick an arbitrary element in this set, Z. Okay. So this is something that I didn't explicitly mention in the anatomy of the proof, but all these propositions that I'm listing, they can be in terms of variables I have introduced. So these are elements that I picked from non-empty sets. So basically, if the set is known to be not empty, I can just introduce a variable and say, let x be an element in the set, and the subsequent propositions can be in terms of that element, in terms of that variable. Okay. So here's what I'm planning to do now. I picked this x, it's an arbitrary element of Z, which means the only things I can use about this Z are actually about this x are things that actually holds for every element in Z. Okay. And what I'm interested in proving for this arbitrary element is a statement. In fact, I'm interested in proving this for every element in Z. So for this particular element I picked, I'm interested in proving this statement. What is this statement? It says, if odd x, then odd x square. So if x is not odd, that statement is already true, right? So if x equal to 10, the element I picked is 10, then this statement is vacuously true. So I'm going to focus on a statement on x's where this is where odd x is actually true, so that there's not going to be a vacuously true. So by convention, I'm not even going to talk about them. I'm just going to say, suppose x is odd. Okay, so I'm not saying anything about those other even elements, 0, 2, 4, whatever. But technically, I should have said for them this is vacuously true. So I'm going to consider other x's. So here there are two cases that I should have written if I were being formal, by being pedantic. But as you will see, and we will expand on this later, in this case, it's okay to start your proof by saying, suppose odd x. Okay, and then the goal is to show odd x squared. So now we use our definition of what x. So these are all steps as a prover you are creatively coming up with. So you decide, okay, I'm going to use the definition of odd. So that says that x is some y such that x equal to 2y plus 1. So this is a non-empty set of y's such that x equal to 2y plus 1. Well, that can exactly be 1. But since I know such an element x is, I'm going to pick such an element. So I say, okay, here's a new variable a. Let a be such that x is equal to 2a plus 1. Okay, a be an element in Z such that x is equal to 2a plus 1. And now I can write propositions in terms of this a. So I'm going to do these propositions are just basically equalities which would follow from the rules of arithmetic that we are going to take for granted. So x square, since x equal to 2a plus 1, x square is 2a plus 1 the whole square, and you know that is equal to 4a square plus 4a plus 1, which you then write as 2 times 2a square plus 2a plus 1. So you got a new proposition, saying x square equals 2 times 2a square plus 2a plus 1. And from arithmetic again, you know that this 2a squared plus 2a should be an integer. There is some integer which equals 2a squared plus 2a. Because a is an integer, all these operations will yield integers. So I'm going to then pick that integer. So I'm allowed to define a variable. So this is the variable b in z such that 2a squared plus 2a equals b. So this is the, I know such a b exists from this proposition before that. And now I can write propositions in terms of this variable as well. So what do I have? I have x squared equals, so I have, b equals 2a squared plus 2a, and x squared equals 2 times 2a squared plus 2a plus 1. Together, they imply x squared equals 2b plus 1. Okay. Again, all these deductions are happening in the world of arithmetic, and I know that I will be able to substitute 2a squared plus 2a by something that is equal to it. So that is 2 times, that's b, so 2 times b plus 1. And then I can go back to the definition of odd, and I have this, since x squared is 2b plus 1, x squared is odd. Okay, so that's my entire rather tedious proof, but the point here is to notice that I showed this for any odd x. I showed x squared is odd, following a bunch of so by listing a bunch of propositions along the way. I'm also defining variables, which is something I didn't formally state, but these propositions, this list of propositions, can use variables that you introduce along the way. Okay, and this whole thing you have to round off by saying, look, I just proved that for an arbitrary element of z, odd x implies odd x squared. Therefore, for every x, odd x implies odd x squared, which is what I needed to prove. Okay, that'll be the, when you write the proof, that's how you will finish off the proof. So again, before I finish, the main point of writing a proof is to make it easy to verify. Okay, coming up with the proof may not be easy. You may need to, come up with creative ideas. In this case, maybe not very surprising, but you had to decide to expand this to a plus 1 the whole square, right? So you have to come up with creative ideas that nobody will tell you, but verifying should be mechanical, and that to kind of segue into a related concept, and this is an important thing that you'll come across in computer science later on, in other courses later on. There is an important question in computer science of which by the name P versus NP. Okay, and this thing about proofs being always easy to verify but may not be easy to come up with relates to that. Okay, so informally, this is not quite the definition. I'm being a little sloppy here, but informally, P stands for a class of problems for which finding a proof or a solution is computationally easy. So there is some program that can very quickly come up with a solution for this problem. So that is what P stands for. And NP stands for a class of problems for which there is an efficient program that can, it may not be able to come up with, it doesn't come up with its own with proofs or solutions by itself, but if you give a solution, if you give a purported solution, it can check it. It can look at it and say there's a correct proof or not, right? So if it is a true statement for which you came up with a correct proof, then your program will accept the proof. It will verify and accept the proof. If somebody took a false statement and tried to write a proof, this program will always reject their proof. right? So suppose such a program efficiently exists, then we call that problem, we say that the problem belongs to this class NP. So clearly, if you could have come up with a solution yourself, if you're in P, then just the act of coming up with a solution is a verification that this statement is correct. So problems in P already are problems in NP. If you can come up with a proof yourself, you are verifying it yourself. However, the converse may not be true. So we think there are problems for which it's easy to verify solutions. So there is a way to write down solutions in a way that's very easy to check. But coming up with that solution may not be very easy, right? And we believe there are problems for which it is not easy to come up with solutions. So that is the statement that we believe that many problems in NP are not in the class P. Unfortunately, this is a claim or proposition that we don't know how to prove yet. It's widely believed to be true. There are a lot of kind of compelling reasons to believe it's true, but we don't have a proof. So for all that we know, the statement might be false. But the point I wanted to make here, I mean, technically this might be false for the specific definitions of P and NP we have in mind, but at a philosophical level, it's an evident idea that yes, for many problems, it's much simpler to verify the proof once you see it, but to come up with the proof yourself is not easy, in some sense of being not easy. Okay. So why it's important to bring up here is your job is to do the hard work of coming up with the proof, so that your whoever is verifying your proof, your TAs or instructor, should have an easy time checking your proof is correct. You cannot make them do non-trivial deductions for you. Okay, when you are asked to write a proof, you have to do all the hard work and make it really straightforward to verify your proof. So what we'll see in the next couple of clips would be different ways of coming up with these proofs. So there's of course no simple recipe for proving every statement. That's true, but here are a few approaches we will be taking. So sometimes the statements would be simple enough that you can do a direct deduction. Many of the, say, formula equivalences and so forth, they're essentially just one-step arguments. But sometimes it'll help to rewrite the proposition. A very important and non-trivial example is proving the contrapositive of an implication instead of proving the implication directly. Another example of proving something else is, instead of proving a statement, you would assume that the statement is false and then get a contradiction. So proof by contradiction. So we'll talk about all of this later. And sometimes it's enough to give an example or a counterexample to prove a statement. So there are statements that admit those kind of proofs. And finally, another very useful technique we will see is of mathematical induction. Okay. So yeah, that's all for now, and we will proceed with these approaches in the subsequent clips.